Welcome, everyone. The event is now live. With that, I will pass the time over to Tim Sherbach to get us started.
Great. Thanks, Victoria. Hi, everyone. Thank you very much for participating in today's webcast. We are going to be talking about some really neat technology, and we're going to be talking about fair data management and storage management in these really neat environment, which requires high throughput pipelines and life sciences environments. We have the great pleasure that we have John Leonardini from Eikon Therapeutics with us today. He is a storage industry veteran with lots and lots of experience, and he is doing some really innovative work at Eikon in support of what turns out to be a massive data, big data type of problem, and really interesting to see the work that they're doing throughout their whole workflow. And John's going to go into great detail about how that works. I'm just going to say a couple, just to keep everyone grounded. I just want to tell you who Quantum is. We are a data and storage management company that is focused on AI and unstructured data across the entire life cycle. And so we focus on solutions that help to accelerate and enrich AI, to store and manage data, and then protect and preserve it over the entire data life cycle. We've been in business for a very long time, have a very big installed base, and quite a deep relationship with many of our customers. And so, as I say, we're really excited that John is here with us to talk more about his environment. Quantum has a variety of different products that provide this ability for us to support the data management lifecycle for many different customers and requirements. Today, we're going to be talking primarily about the Myriad all-flash storage system, which is a multi-protocol, all-flash, new design dedicated to high performance and workload consolidation. And then we will be talking about the ActiveScale object storage system, which is an object storage solution with multiple classes of storage that provides for very high performance and yet cost-effective performance, all within the same namespace, and so provides for easy access, protection, and retention of these massive data sets that we'll be talking about today. Just to put this in a little bit of context as we start to explore Eikon's environment, what is happening in the industry today is, of course, that we have a variety of these different high-performance computing, analytics, and AI-type workflows that require some amount of storage dedicated to the ingest and a workflow that focuses on the ingest, data preparation, model training and analysis. With AI, of course, we've got data inferencing capabilities that are part of this workflow, and ultimately archiving of data that is ultimately increasingly required that data be archived forever. And so there are very big demands on the storage infrastructure and the data management infrastructure. And so what you see evolving within many different customers is this data management infrastructure layer that provides for the cataloging, discovery, and search of the data, providing for the access and authentication to make sure that data is protected securely. And then ultimately, this becomes much more of a DevOps environment in which there are a variety of APIs and data integration tools and middleware that are applied in order to support these very interesting and complex workflows that exist. In Quantum's world, we see Myriad and ActiveScale playing key roles in this, in that Myriad is the production storage for very high performance data access, and we use multiple protocols and an NVMe based scale out architecture to support that. And then likewise on the ActiveScale side, this is really in today's terms referred to either as a data lake or a storage cloud or an active archive, which is primarily an S3-based interface and uses a combination of NVMe, hard drives, and tape resources in a single namespace to provide very effective, cost-effective storage for the long term within this environment. So with that, I'm going to hand it over to John to talk a little bit about Eikon and his environment as we go forward. There you go, John.
All right, thank you, Tim. Well, you just missed the title slide. It says, who is Eikon? So I have found there are two groups of people in the world, folks who I say, yeah, I work at Eikon. They go, wow, cool. And then the much larger group was like, Eikon, never heard of them. We're a fairly new company. We actually were incepted during the pandemic, and we were founded by a Nobel Prize winner, or co-founded, a couple other folks, who made some breakthroughs in optical microscopy that allows us to do some pretty amazing things, looking at what's happening inside of a living cell without blowing the cell up, basically. Now, this is where I'm going to give my standard disclaimer, and I'm going to say, please keep in mind, I'm a storage nerd. I'm the guy who keeps track of the storage. I am not a scientist. I know what you're going to see here as far as our technology from what has been relayed to me by very smart scientists, but if you want to ask me, go very, very deep into single molecule tracking technology, I can kind of scrape the surface. But what the proposition here is, Eikon has got this technology where they can look inside of a living cell, watch the interaction with a compound or something that's been introduced into that cell, and see how the various proteins interact in this particular case. The technology has got broader applications that we're also working on, but in the course of this conversation, we're mostly good talking about the SMT technology that has been used for oncology or cancer drug research. Now, Eric got together with some other very smart people, and they mashed that super resolution microscope along with some robotics, and then some other very smart people who work in high performance computing and supercomputing architecture, and put all those things together and created kind of the data pipeline that we're going to talk about here. So I'll let you read the slides because they've been up there for a while, but that's basically what we're doing. We're breaking inside of a cell to look at interactions of specific compounds on proteins within the nucleus of that cell. And what's cool, we actually have, this is a single well within, and what you're seeing happening here is this real-life tracking of these of the molecules within the nuclei of the cell and the tracks that they go on. Basically, the concept here is by looking at how they interact with each other at the speed at which and the time it takes at which the scientists can make inferences with regards to what is going on within that, and that informs the research that continues to go into various compounds that we are developing. This is video that was created, like it says here. This is from what we would call a single FOV or field of view from a single well. We'll talk a little bit more about the scale of the problem, but a single FOV from a single well, that's a very, very small piece of data from the overall pipeline standpoint. So Eikon does have custom-built hardware. We build the microscope technology, the hardware that allows the single molecule tracking. We have a very, very large and very, very good software team that works on the algorithms to actually tease that data out of the information that's coming out of our microscope platform, and then the various chemicals and such that make it possible to actually see these interactions that we saw on the previous slide. We do very much think that, and this kind of informs where we're going to go. We're using this suite for very specific pharmaceutical research into a couple of different life sciences problems that are very significant. The technology itself, both the hardware and the software and the reagents, all have use cases far past what the therapeutics portion of the company is working on. I keep clicking the next thing and I have to kick the button. So this, on a slightly different platform, you would get to actually see these guys working, but this is a still shot of what we would, one of the pods on our factory floor. If you're looking around, you see some stuff that may look sort of familiar. If you're working in a life sciences lab, you can see a cytomat and that sort of thing. The white chassis to the front, those are actually the frames for the microscopes, and the carts they're sitting on are below. And then you see the robot up there that keeps those things fed. The horizontal plates there are plates. Each one has got a large number of wells on it. Each well will have a compound in it. And this automated process will move pretty much constantly. We're almost constantly in production, screening these compounds in real time in order to facilitate, like it says there on the title side, the purposeful integration of engineering and science. Couple of slides here that kind of the sort of information we're looking at here is the motion of the proteins, and as we look at how they're moving as compounds are introduced to them, we can make we can make decisions based on the efficiency of the whatever compound is with regards to the that particular cell. So here, this is actually you're watching that's actually a 2-second movie going on there. It's kind of sped up for this, and the interaction that we would be getting out with regards to the dynamics. And this allows us to pull out a lot of different information around the various functions in the proteins. Now, again, if you wanted to learn more about this technology from a science standpoint, I would urge you go to the Eikon website and check that stuff out. It's very, very interesting. I am not a scientist. I'm an engineer, and specifically, I'm a storage engineer. So a lot of this stuff about small subpopulations of proteins by disrupting protein-protein interactions, yeah, we absolutely do whatever that is. Now, we'll talk about where this comes in for me. If you were to look at this pipeline, each particular plate has got hundreds of wells in it. We're going to capture between 200 and 1,200 frames per second off of a 2-second movie within there, and we're going to look at that frame by frame. This turns into literally billions and billions of points of data. We have this data that we are using for our research, but again, we're looking at very, very specific use cases, but we're looking at basic building blocks for life, proteins. And our data has got relevancy outside of our narrow use case. So the National Institute of Health came up with a concept for research data that they call FAIR. And from some of the questions that we got asked preliminary to the show around usage of FAIR data and everything, I think some of the folks who are on the call are probably familiar with this concept. It's not what I have learned in the storage industry is FAIR is a concept that is coming online, but it makes perfect sense, right? Data, research data, particularly we're trying to find the cure for cancer here, should be findable, it should be accessible, interoperable, reusable. In other words, if you're generating research data that, particularly life sciences stuff that's for the benefit of humankind, the fact that you can find it, access it, use it, and reuse it, all sounds like pretty good things to do. And the purple boxes there are some of the guidelines from the NIH with regards to how FAIR is. So I was introduced to this concept a little bit over a year ago by one of my counterparts on the software side of their team, because they started talking about FAIR data. At the time, it has the word data in it, so I have to worry about it. Didn't know what FAIR was, started doing some research, understood it to a point where I could tell you that from a storage standpoint, the stuff that I've highlighted here kind of land firmly in the storage area. These have some sort of globally unique and persistent identifier. I will share with you that is not standardized yet, what that globally unique and persistent identifier is going to look like. Metadata is going to be key to this. You're going to, in order to be able to find it, you're going to need to be able to search, query metadata to pull stuff out. Now, accessible, that's what we do in the storage world. You're going to look at retrievable methods based on that metadata. It's going to need to be a universally implemented protocol, and the metadata can be indexed separately from the data. All of this will kind of key into where some of the quantum technologies fall into our use case. Interoperability is primarily, from my standpoint, it needs to be kind of a shared, broadly understood language. This is more of a software implementation thing. And then reusability, okay? Provenance is going to be important. You need to know how that data came to be, and it needs to be domain relevant. Now, on the converse side, for software folks, some of these things are very much in the software world. How the data is described with rich data, metadata, for example, and all of these things kind of hit in the software world. So this is not something that the storage teams are going to solve on their own. This is something that the storage teams need to look at in the course of a larger conversation with their internal or external customers. The software engineers are actually working with this data, whether these are research scientists who are accessing this data a certain way, or in Eikon's case, the folks are actually implementing these algorithms. So I kind of break that out just to kind of make sure. Now, the question that was asked at the kind of the head of the show, I'm going to read it out from James. Can you provide examples of how FAIR data principles have enhanced collaboration or reproducibility in life science research? Can I give examples? No, because I am a storage guy. What I can tell you, why it matters, is what the National Institute of Health says. And I want to call your attention to button number 5. If you rely on grants to fund your research, FAIR data presentation, being able to say that your data is presented in a fair manner, is going to have everything to do with actually being able to secure funding in the first place. The basic tenets I'll share with you is just something that, to my non-scientific mind, just makes sense. We need to think about FAIR data. We need to look at the stuff from the National Institute of Health and others with regards to how we curate this. What is being built at Eikon to a very large degree. We are embracing FAIR early, as we currently have, just approaching 3 billion pieces of files, but someday it's going to be a lot of data. That was sarcasm. But we need to implement that now, because the further down the road you get without thinking about this stuff, the harder it is to come back, block file trees or whatever, come up with the unique identifier standards and and apply them, that mine out the metadata correctly. The bigger the data pool is, the harder it is to do this retroactively. It needs to be part of your pipeline. Now, last slide on this. This is a little bit of a commercial for fairsharing.org. This is where my counterparts in other life sciences organizations, if you are not up to speed on FAIR, start here. There's a lot of use cases. I will warn you, what you will find is that FAIR is not a standard. FAIR is to, I could almost compare it to, like in the financial world, Sarbanes-Oxley, where no, you don't have a storage platform that is Sarbanes-Oxley compliant. You have business processes that are Sarbanes-Oxley compliant, and your various storage technologies are basically part of a balanced breakfast, right? They enable that presentation. Okay, now, how do we do this? Okay, so this, and I did have to change for various reasons our internal naming schema, but I kept some of the first letters and first names for how we qualify this. So over there, Zoltan, that's my tier 0. Quantum Myriad is one of the platforms we use primarily actually for scratch space in this environment right now. We find it to be very performant for NFS style presentation. There are some things that are on the roadmap for Myriad, we'll talk about here in a little bit, that we're very excited to have to implement that will strengthen the story for Myriad. We have, actually, I can say authoritatively, we have the longest history of Myriad of any customer on the planet because we were one of the early access testers for this product, and we liked it enough that where we moved it into production as a tier 0 all-flash storage. I like the architecture. I like the fact that that is really a scalable key value store in terms of addressing. That enables a lot. Some of the things that are upcoming as far as a POSIX driver for parallel computing is going to greatly strengthen that particular product. Now, from there, the pipeline that's coming off the scopes lands on one particular storage area, which is the raw data repository. Now, in raw data format, we throw off a incredible amount of data. Like it says, 800 terabytes of data per scope per month. We currently have in excess of 20 scopes running in production, being fed by robots all the time. So that data is coming up. Now, the raw data, in some cases, we will have needs to hold on to the actual raw data, but this is science. We do actually capture how the methodologies work that we captured that data, so it can be recreated basically from the cookbook or the laboratory notebooks that's associated for that particular data. So generally speaking, stuff that is stored on the Alice tier is not stored for very long. We have a short SLA that we store that data, except if a end user, internal customer, external customer says that they need to hold on to that data for whatever reason. I honestly don't ask why. I just say, okay. And then we have some other stuff that we'll talk about. And then from there, we're going to process that through our high performance compute cluster. And that is going to write off to the process data repository, here referred to as Antoinette. And you see there, the retention SLA is a very bold forever. Yeah, so that's cool. Forever is a very, very interesting time. There is, if you do the math between the raw and the process data, you see that there is a huge amount of reduction that happens from the raw data we generate and then the process data that comes out of the high performance compute cluster. Internally, to keep track of a lot of this stuff, we use a product that I think very, very highly of. not from Quantum. Quantum has got great interoperability with it. Is a product called Starfish. And this is what we use as a very high-speed file walk reporting and audit server. So that is considered my single point of truth for what is going on in my various environment. We have an internal data mover that we built that leverages the capabilities of our various storage platforms. It's parallelized. It's very, very fast. It can speak from about anything to about anything, and it can leverage some of the internal capabilities of our various storage. The data mover will inform Antoinette to put a second copy of the process data off into a second tier, here referred to as Barbara. That is really a staging environment for what happens next, which is an offload to S3 compatible object storage. Now, going back to FAIR, if you think about the tenets of for FAIR, in my opinion, it's just my opinion, object storage or API addressable technology rather than protocol-based technology is key for implementing FAIR. Because, now S3 is not a protocol, it is an API. In other industries, we've used API address storage. Matter of fact, before we called it object storage, back in the days of Coringo and EMC's Atmos and whatever, Centera product, that was just API addressable storage. And it was intended as a relatively low-cost, very robust means of storing the data. In Quantum's case, they have the active scale, which meets that need for S3 compatible presentation that we can keep in-house. Part of the idea here also is that our data mover can do the information to put that data off onto about any kind of storage we choose to. So we will use a variety of cloud providers, and we will also have our internal repositories. Depending on your cloud provider, actually working with data that is off stored on some remote cloud may be a sort of an expensive thing to do. Having the storage on-prem in S3 compatible, hot, cold, tier cold, prefetch enabled mechanisms such as ActiveScale allows us to serve the needs of now and future, like it says, globally dispersed, hyper-intelligent researchers. So that's sort of what we do. Going back to Myriad, this is a slide that I've frankly cribbed from Quantum, and it does, I'll point out, it does call out a couple things that are in early access with the product right now, such as that POSIX client that we're really, really looking forward to. I've seen a lot of storage in my career. Myriad, the basic underscoring architecture, where it says right there at the bottom, that foundational transactional key-value store enables a lot of functionality that will come to pass in the future. Presentation that comes out, the various, NFS clients, SMB clients, everything, they're all very good. In our case, for how we're doing, as a company, we actually, I as a storage engineer, actually prefer client-side drivers to relying on industry standard protocols. And some folks dig in their heels and go, oh my God, you want a client-side driver. Honestly, in our case, any system that is accessing this data is probably going to be a corporate image anyway. And I'm sitting here looking at my corporate laptop, and I have got a VPN connection and an antivirus scanner and a few other things. Oh boy, okay. And I will give my co-providers a heads up that we've been working here long enough, and I have no AC power where I'm at. So I'm at about 20% battery, should be okay. If I suddenly go away, that's why, and I won't be back if that happens. So Now, Myriad, this is actually this is a slide from the marketing area there. Myriad is a hot data tier. Like I said, we use that primarily for Scratch right now for our high-performance compute cluster. Our Docker implementations run on top of that thing and a few other. What I found for it is for NFS, very, very fine client. It's got one of the nicest snapshot cloning replication solutions in it already in the product that I've frankly seen in the NAS space. I would put it toe-to-toe with anything else as far as the data protection sphere, which is a little ironic since I'm using it for Scratch. But there's good architectural reasons why we're doing that. Now, Amy, this is where the cure for cancer is ultimately going to live, as far as I'm concerned. We have implemented quantum active scale. Quantum active scale gives me the functionality that we would look at from any S3 compatible product. I have a hot tier that is built on all NVMe nodes, fairly powerful. Each one of those guys that you're looking at there has got 24 7.92 NVMe drives in it. It's about a little under a petabyte usable capacity after erasure code for that. That serves as the hot tier and actually the storage area or the tape staging area for the underlying quantum rail technology tape library. So we have 5 quantum robotic tape libraries, each one filled up with LTO9 tapes. Right now they look exactly like you see there. What we like about that is we can actually scale that up very, very effectively. Now, I will acknowledge it's 2025, and I just told you that I think tape is a good idea. I stand by that. If you were to actually look at the problem of I need to keep this data around forever, and most of it is going to be stone cold, possibly for years at a time because some researcher is not accessing that. Quantum rail tape technology allows me to basically erase your code across those various libraries so the data is well protected. It's accessible. It can be warmed up back into the hot tier for data sets that are active. But a good portion of this data is, like I said, maybe cold for years and years at a time. It scales up very well. We like it a great deal. Now, because our presentation method is what it is, we can also send this data off to third-party cloud providers for presentation elsewhere. The big thing, interoperable to me, as I said before, really means some sort of object storage. So, yeah, and that is our implementation of active scale. So this slide actually came off from Quantum, so I can let Tim comment on that a little bit more. If you want to learn more about Eikon and what we're doing over here, it's a fascinating place. I will share with you that they were actually my customer as a storage, pre-sale storage engineer, frankly. And after I really wrapped my head around what Eikon is doing and the capabilities that they are bringing to the life sciences world, I said to myself, that's what I want to do. I don't necessarily want to build the next whatever, make another social network or whatever. Hey, let's go cure cancer. That sounds like a better thing to do. And Eikon and Quantum, that's, by God, that's what we're trying to do here. Tim, anything to add?
Yeah, thanks, John. That was a great presentation. Yeah, what I'd like to do before we close out is just head back to this slide, which kind of describes your environment. Let me go back a couple slides, because a few questions have come in, and I had a few questions that I think are really interesting. First of all, here you are with one microscope and basically having a requirement of at least 65 terabytes a month being stored forever. But can you comment? When you think about the scale that Eikon is looking to achieve in terms of these the microscopes and the amount of work that they're doing, what is really the scale in terms of capacity that your storage requirements actually require when you think about it as you move forward in time?
Okay. Well, so you have the data that's coming off the scope, and we gave that number, and that number is a approximation based on current resolutions, what a scope is capable of doing per plate if it's running at the schedule that it runs at. We have, like I said, in excess of 20 scopes in production right now. We continue to put scopes up. Now, fun fact, actually right now, even as we speak, Eikon is moving into a new headquarters building. We're located in a very small building in Hayward, California. We started building our new headquarters a couple of years ago, and we are actually literally occupying it right now. That's going to give us the ability to scale much larger. I use the number of scopes indicates the SLA that I can preserve the raw data, if that makes any sense at all. I can look at, okay, so we have this number of scopes. They're going to produce about this much data per scope. And particularly in the current facility, we have this much room, this much power, and this much cooling to run that stuff. And therefore, we can have this kind of SLA in terms of retention. What we have found, if you do a lot with a little for a long time, eventually learn you can do anything with nothing at all. What we have learned is our SLA is very, very tenable. And so long as we engage in very, very smart enforcement of our SLAs in terms of retention, no one seems to bother. I do want to point out, though, so we have the raw data. And when that raw data lands on its repository, the clock starts ticking from C time. It is not based on M time or A time. We go right off of C time. So C in this case means creation. So 6 weeks or thereabouts from creation time, that raw data is going to not be there anymore unless a researcher says, yeah, that has got scientific significance or whatever. Someone comes in and says that particular piece of raw data, that needs to be retained for a long time. That triggers a different workflow that puts that archived data ultimately directly onto the active scale cold storage tier where it can be accessed as needed. Now, if someone continues to work for that, they may have to heat that data up, and that's where the flash layer comes in. They're going to be addressing that thing, reading it out off of NVMe, so it is very, very fast. Or it may just be something that, for whatever reason, we need to keep track of that raw data forever. And the means that we're storing the cold data, the cold tier, was architected. It is not technically forever. It is 200 years is what that system is rated for. It's an incredible number of nines, 200 years data retention. It is an erasure code schema that goes across libraries, and the reason we implemented as many libraries as we did is so that we have the flexibility. We could lose an entire library, we could lose an entire rack, and we have not lost access to any of those files because, again, we're trying to protect the cure for cancer here.
Right. Wow. So, really, it's kind of a scenario where, I know the active scale today is about 6 petabytes in terms of capacity, but over time, you're looking at tens of
Ask me that question.
George.
Ask me that question in March. It will be more than that.
Yeah, exactly.
Again, we're getting ready to move headquarters, so we have enough landing zone on that for presentation right now throughout the move. It will be scaled up very, very shortly thereafter. And yes, it's architected in such a way that it will be scaled up. I don't know when we're going to cross the exabyte threshold. I can share with you anecdotally that if we didn't have the SLAs around raw data retention, we already would have crossed an exabyte threshold. And that's, frankly, particularly in our current facilities, that would really not be tenable. And particularly since the meat and potatoes of the data is not the raw, it's the usable. But there it is.
Right, right. So a couple of other questions. So in the beginning, I think you were using a lot of cloud storage, and I imagine that when that gets pretty expensive. And so was that kind of an impetus for the ActiveScale cold storage system as you started out?
Well, not to break my arm patting myself on the back, but frankly, we negotiated a pretty decent deal with our cloud provider in terms of cost per terabyte per month. But long term, there's a few challenges with the particular public cloud providers, and we still use a public cloud provider for another copy of this data. And this is basic data curation tenets, the old 1, 2, 3. One piece of data is on 2 different platforms in 3 locations, and now we are sure that no matter what happens, we have got a recoverable copy of that particular piece of data. In the case of the public cloud provider, it was a functionality thing. It was a latency thing in that time to, and it was a performance thing too, because our ActiveScale is wicked fast, and the public cloud providers that we're using are okay. But that's as good as it gets. They're okay.
Right. There's a lot of bandwidth requirements when you think about an external cloud provider.
And yeah, so we've got very large bandwidth. The other thing that I'll point out is when you're talking about doing computation against it, if it's API address storage like this, there's read, append, write cycles. It masks to some degree. But if your data is up in the cloud, you're also going to have your computation in the cloud. I read about solutions where, oh no, your hosts will be on-prem and they'll access data in the cloud. And there's this thing called the speed of light, and how fast, the latency that is involved in that sort of thing honestly gets untenable very, very fast in my opinion. So in order to stay connected to the high performance compute and the storage, having the storage on-prem just makes sense. And then the other thing I'm just going to say in general about public cloud absolutely has its place. I like to compare it to a hotel. I stay in a hotel when I have things to do that I can't do at home for one reason or the other. It is very, very expensive to live in a hotel. The cloud is a data hotel. It makes perfect sense if you're going up there for burst capacity to do some computation because you need access to X number of GPUs. But if you look at long-term data retention, our cost avoidance by moving this on-prem versus keeping the permanent copy of the data in public cloud it's a very, very large sum of money. It is 6 approaching 7 figures of cost avoidance.
Fair enough. A couple other key concepts I wanted you to talk to is one is in relation to software-defined storage in your modern IT environment, and then as well kind of the concept of scale-out kind of platforms and how they are important when you
Okay.
think about the scale that you're growing to?
All right. So I will tell you, my computer is telling me it's going to go to sleep very, very soon. So this may get cut a little bit short. But
Okay, this may be our last question.
It may be software-defined storage. Everything that I do, implement is software-defined. We implement on standard storage optimized platforms, right? But we have got standard internal platforms that we use for hybrid flash disk and all flash nodes. And part of our qualification for any software system is that we qualify against this hardware. The logic there is we know this is good hardware, right? This is go right down the line, I will check off. So as we were to compare, say, when we were comparing our tier 0, I was able to run exactly the same benchmark against 5, 6 different file systems and be able to authoritatively sort them out with, given the same hardware node to node, this one does this best. This one is slower from latency. This one, right? So we understood, and we're kind of getting the hardware out of the picture. Frankly, that's a cost avoidance thing also by working with the hardware vendors directly. My opinion, we're getting better optimized hardware, lower price, and we use file systems to work with it. The quantum active scale, for example, that's running on the same flash nodes that I use for a portion of my tier 1 storage. It's exactly the same hardware. It's just what software is running inside that guy. Scale out, the only thing that makes sense. You're not going to scale up in my environment. Generally, I can't give too specific, but I can say it's bigger than. It is bigger than 20 petabytes. It is bigger than 2 billion unique objects within the environment. It's huge.
I really appreciate, John, our participation today.
Any other questions in the queue at all? I'm going to milk it till my battery says it's 9%. So if you've got anything else, goes dead.
I think we're all set there as far as questions in the queue. I mean, there's certainly more questions than I have. I mean, if you think about, the modern definition of a data lake, which is a little bit nebulous, but to what degree does that whole concept, and when we think about fair data management practices and a data lake, what do those kind of impose maybe in terms of your storage requirements?
Okay, so data lake, lake house, this sort of thing are, sorry, Tim, they're marketing terms for very large data repositories that are addressed by one way or the other. Okay. Am I sitting on a giant data lake of single molecule protein interaction data? Absolutely. That's, again, that does get into, from a presentation standpoint, if I look at that, that is something that a researcher is going to be addressing at an object layer. You're probably not going to go after that from an NFS or, God help you, an SMB protocol layer, because it's just too big. Caching is going to get weird. You're going to struggle with that. And frankly, you're probably going to violate interoperability things. So from a presentation standpoint, what the marketing folks like to call a data lake, that I would just call as a great big bolus of API addressable data. Yeah, sure. Do that. Absolutely. If you want to call it data lake, that have a lake house that lets you address the data lake, and then, I don't know, have some data water skis that allow you to fly around the data lake and throw up some data wakes and throw data onto other data or whatever, that sure, go for it.
Yeah. Well, let me ask it a different way then.
Data water skis.
Yeah.
Okay, so you heard it here first.
Yep. Well, let me ask it in a different way then. It's certainly I imagine in some ways, I don't know how your software team is architected, but there must be a lot of emphasis on data management in terms of how across all of these billions of objects are we going to manage that in a cohesive way such that we can reap the benefit of that data. And I'm just wondering kind of what are the key tools or technologies?
Most of the very key technologies are home built. These are very, very specialized for what Eikon is doing themselves. The presentation is very uniform, and it is built in such a way, frankly, that we're independent of protocols. We're independent of presentation. It may require a little bit of refactoring, but that was kind of taken into account when this stuff was built. That would be most of what I can say. The actual tools that we use to address this right now, we have some folks who are using some cloud-based stuff, but most of the research stuff actually comes out of a few home-built, very, very specific database style architectures to locate data down to a single FOV within a single well. As that slide that you saw earlier was actually output that came out of one of those internal tools.
Right. And is there a query language that's kind of intrinsic to the environment then? That
I honestly could not answer that question.
Okay.
Sorry. I can tap dance close to a line. Certain lines I can't cross. That would be one of them.
Perfect. All right. Well, why don't I close it out, John? Number one, thank you very much for all the effort that you've put into this webcast. I really appreciate all of your expertise and all of your sharing in terms of your environment and kind of what you've learned along the way, especially as you're building such a massive storage infrastructure in support of some really critical work. So thank you so much for that. Just to close out, I think a few things to consider for the audience is, just as in Eikon's case, that there are these digital sources that are driving just massive data sets, and they obviously have great value if we can harness the data and apply, new generations of analytics and AI and in order to drive additional value from those data sets. One of the things I think that's key, as we talked with John, is that fair data management is really essential for automation and gaining the most data value across your workflow. If you go to the Eikon website and watch some of the videos to show the level of automation that is in their environment, and when you consider the amount of data that is being collected by the Eikon workflow, it's very clear that, hey, you got to keep track of this data, you've got to make it accessible, and just have a strong data management strategy that is going to allow you for scale and automation. As John talked about, scale-out storage is really key in order to optimize your storage environment and just being able to continuously scale as time goes by in order to manage these large data sets. And one thing, of course, that John was very emphatic on is that, hey, flash, disk, and tape all have roles within the environment, and that you've got to deploy these strategically such that you're getting high performance across those elements of the workflow that really require high throughput, low latency access to lots and lots of data in order to be able to efficiently process and analyze the data. And then because of these requirements that are, we're in this scenario where we're going to keep data effectively forever, we need to be able to use low-cost mediums as well. And one of the key elements in all of this is in order to grow and migrate over time, it's important these scale-out architectures are the vehicle by which we can adopt new generations of technology and decommission old generations of technology and keep all of this data in place over the years and decades that are required. And so, therefore, it's really important to think in terms of storage platforms that are able to scale and grow and evolve over time with next generations of technology. So with that, I want to sign off. I want to thank John again for his participation. There are several materials that you can download from your webcast console. And then if you want to learn more about Eikon and their capabilities and the technologies that John talked about in some detail, I invite you to go to the Eikon Therapeutics website. And then, of course, quantum.com is available as a resource as well. Thank you very much for your participation. Really appreciate that you took the time out to spend time with us and talk about some of these great technologies. And have a great day. Bye now.